the membrane. And that's because the enzymes that catalyze these reactions are stuck in this membrane. Okay, so that's why it's going to occur there. Now, we know we start with NADH, right? So NADH comes in. Now, these arrows don't represent moving. These arrows represent a chemical reaction. So if I do this, I'm not saying that NADH moves from here to here. I'm saying that NADH gets oxidized. You with me on that? Is that okay? Mm-hmm. So I'm not trying to say it physically moves anywhere, but it gets oxidized. Now, ultimately, and I'm going to summarize this, what there is, or where this is happening, there is an enzyme complex, protein enzyme complex here, where all of this is occurring. Right? And what's happening as that occurs is that this electron is being kind of bopped down through here from compound to compound within that complex. And ultimately, what that electron is going to get passed to is going to get passed to Q, right? And that's the oxidized form of Q there. And as Q gets the electron, let's do it this way since we're talking about hydrogens being our way to carry electrons, it gets the hydrogen. You okay with that? Does that seem all right? So that's an oxidation. Q gained the hydrogen electron. That's a reduction. Is that okay? And this pair, this coupled series of redox reactions right here, is exergonic. And if embedded in this protein complex here, as this electron gets passed through, is a proton pump, we can pump protons, which are hydrogen ions, right, from the matrix to the intermembrane space. Is that okay? So now who's got the electron? Q. So we want to give it to something. We said, well, we give it to a cytochrome C, but again, there is this other protein complex here that catalyzes all of these reactions. So Q is going to get reduced or oxidized, QH. Oxidized, so we're going to come back down here. So it's going to come back to this, right? And guess what? It's going to then grab another electron and just keep doing this. So what's Q doing? Taking an electron from this enzyme complex and giving it to this enzyme complex. And then that electron will bop down through here now. E negative, E negative, E negative, until ultimately we give it to something we'll call cytochrome C. And cytochrome C, that's the oxidized form, is now going to become cytochrome C, I'll put the H there, the reduced form. So oxidized, it's going to get reduced. Reduced, it's going to get oxidized. So that's the oxidation, that's the reduction. You okay with that? And then every time these redox reactions occur here, that also is exergonic, right? Redox reactions are exergonic. We're going to use that again to pump more hydrogen from the matrix to the intermembrane space. Is that okay? Now who has the electron? Cytochrome C. So we need to give it to something, right? So it's going to, again, get oxidized back down to that. We have another enzyme complex right here where we pass that electron through this. And then we ultimately give that electron to oxygen. Here, as it gains the electron, it's not balanced, but as it gains the electron and the hydrogens, it becomes water. That's the reduction. So if you reduce oxygen in this context, what do you produce? Water. This is redox reactions again, overly exergonic, right? So what do we want to do? Pump hydrogen there. Now at this point here, we have completely oxidized glucose, the carbon dioxide, and water. But the energy is not in ATP yet, is it, right? The energy is stuck in this concentration gradient where we have a high concentration of hydrogen in the intermembrane space and a low concentration of hydrogen here. This is where we want to use that, what we call that proton motive force through ATP synthase here, right? Here. So now, as we let hydrogen diffuse down through here, that spins that turbine and that drives this reaction here. ADP plus PI gives me ADP. Is that okay? Now, and it's not until then that the energy that came in over here in food, it's not until that point that after you ate your double-double, right, that you make any ATP from that. I mean, granted, we made a little bit by that substrate level in glycolysis and the citric acid cycle, but not very much. Per molecule of glucose, right, we had 2 ATP in glycolysis and 2 ATP in the citric acid cycle. That's not very efficient, right? Because we see that if we do this here, oxidative phosphorylation via chemiosmosis is what I would call this that I just described. This is oxidative phosphorylation. Doing phosphorylation with energy from oxidations, right? Hence oxidative phosphorylation. We use a proton motive force, right? That protons move that generates the force to do this. And this whole process of pumping hydrogen and establishing this electrochemical gradient and then having it diffuse is called chemiosmosis. So you will see those words get used a lot kind of interchangeably, but they're kind of